I can to time. Okay, I retain the last right X and the last X1 and what is it? But don't forget about X1. But you right if you X here, I mean it can
大失败，什么考？Hello. Hi. Could you hear me? Right. Things become so unstable today.
me?
Not very stable.
Yes.
The signal.
I don't know why. So let me switch to other things to see if that's better. Oh. Hi. Um. So I will keep trying. Could you guys hear me? Okay.
Yes.
Yes, thank you. I guess. Okay. I think they are recording right now, and let's just try our best. I don't know what happens. It's so unstable today. And then, okay. I'm trying to say right here is you can change your xn to yn. Then you could have in that the Rabin variance of yn at. Okay, and then yn again, y1 to yn. The same thing right here. EYN, then you type in YN. Okay, it should take him bunch of time and then patience to derive in the variance of y to derive variance of y in it. Okay, so then eventually I think I can give an answer if you want. Well, you have solution key, so I feel like you can check in solution key and see what happens. Okay, but I do want to point one thing out. It's eventually two things I want to point out. One thing is this is a sense of statistics. Basically means that covariance of x1 and xn. Imagine when n goes to infinity. I do mention that before when we are doing some homeworks. Okay, so imagine when n goes to infinity, you do have something, for example, from 0 to 1, even from, I think the same. Okay, binding means it's the same, which means that it's, if you do have that x1 to xn in some range from 0 to 1, okay, even if this guy goes to infinity, I think will be fine. Okay, by any means, I want to say one thing. You might remember I mentioned that before. It's as long as you have many things happening in between, right? N goes to infinity means you do have bunch of the observations between your 0 to 1 edge. Okay. Imagine your dependency between smallest one to largest one. Okay. So by those ordering things, okay, it's not hard for to imagine x1 and x2 will be more dependent between x1 and xn, isn't it? Okay, so that means your neighborhood is going to become more dependent. But imagine whenever your neighbors are really long away from you, then you actually have nothing to do with that. Dependency actually decreasing whenever you order statistics in terms of distance. Okay, so that means these two guys would be more dependent with these two guys. And then not hard to imagine, as long as you have dependency so long away, this guy right here is going to become 0, which means it's your minimum order statistic has nothing to do with your maximum order statistics whenever there are so many things happening between two statistics. Okay, then these two guys are easy to work on. Okay, then I told you that eventually the variance of the n plus 1 then divided by 2n minus 1. This is unbiased estimator I find using R. And then that guy eventually would roughly become, if you take this guy out to 0, this guy would become eventually, I think, a lot of complication. Eventually you can do this square. Okay, so this guy even simplify one. Okay, because I can you can see a solution here, right? You have a middle one which basically is two guys come together. You have these two guys together to become some variance. Guys, even simplify one. The reason I want to write so, I want you to specifically looking at the variance of the two guys. The variance of t divided by n, the variance of r in terms of unbiased statistics is divided by n squared. Divided by n squared. You guys see that? 1 divided by n, t, rt divided by n divided by r divided by n squared. Okay. This is common sense in statistics. Okay. Imagine your variance is actually measure what your precision of estimation is. Okay. Imagine one estimation is divided by n. The other estimator's variation divided by n squared. Let me ask you, which one shrink more quickly? Okay, remember I told you, how do you show an estimator is consistent of estimator? You can take your expectation, right? Take a limit, then become theta. Then another condition is what? You take your limit of your variance that goes to 0. Okay. What told you that if your variance goes to 0, that means your estimation shrink to the theta, right? And then imagine why people would prefer this guy right here compared to this guy. Okay? The reason people like this guy right here is the variance shrink quicker of R and T is. Okay? Then technical speaking, would be so less. We will say this guy's root and convergence. Okay? Because this guy divided by root n is standard deviation, right? Or in the MLE, you see that MLE is root n times sigma squared minus sigma goes to D, then normal 0, I1 inverse. I1 inverse. Remember that? Okay. So basically, in terms of MLE, this guy's root n go down to the variance, roughly divided by n, right? So we call it root n convergence. Okay. And then right here, this guy right here, basically it's n convergence because when you take square root, that becomes n. Okay, that tells you that it's this guy shrink quicker than this guy, and you will prefer some estimation shrinking quicker than the other. Okay, good. So that's the reason why not only about R is a function of the sufficient statistics, but also R having quicker convergence than T. Okay, good. So that's a 1. Any question on 1?
Hi, I have a question.
Yes, yeah, go ahead.
About this take-home part.
Yeah.
How do we know if we could use approximation like
so,
this?
It's only for comparison. So you do your best to do comparison. Of course, you can derive in the variance exactly what that is, right? So you could actually deriving the R, so the R's variance or the unbiased estimator of R is. You can for sure deriving your variance under exact sample size. Then you do your comparison based on which one have showed smaller variance. Okay, and then but sometimes if you don't have so much tool, then you are trying to make some sense of why people would prefer one or another. So approximation just give people a sense of that, a sense of discussion, a sense of easy discussion for people to see why I would prefer one than the other.
I see.
Does that make sense to you? Yeah. Right here, just you can imagine a way saying it. Yeah, go ahead.
I'm just concerned about if in the exam and I'm faced with such a question,
Right.
should I derive the explicit form of the variance, or should I use the convergence theory?
So I would have told you one way or another would be fine. So which means it's as long as your approximation making sense, as long as everything looks so feasible. For example, like I said, it's the covariance of x1 to xn going to become 0. That making sense to me. And then you're deriving. So a perfect answer would be you're deriving every component. Okay. Talk about which I have smaller variance. That's a perfect answer. Okay. Then especially you have your of that, then you either do ratio or do difference. Right? You talk about it's bigger than 0 or bigger than 1, something like that. Okay, that's perfect approach. Okay, but some especially exam, and then you could think about approximation, and then you could think about as long as you do anything, make your argument logic. Okay, so I usually put this kind of question open-ended. Okay, unless I really show that you could do little things to showing that one is bigger than the other. For example, emitter number 2. Okay, then is not reaching their model bound, right? So that one's really easy. Saying it's your exponential x is bigger than 1. Oh, your exponential x minus 1 is bigger than the other guys. So if it's that easy to show the comparison, I'll ask you to do so. But in this question, it's actually not that easy to do so whenever you have so complicated function of n's for their theta square, something like that. In that sense, I will give you something easier than you. So again, it's
sorry, I can't hear you very clearly.
So if you could do, okay, so say it, but you write something down, making major points. Okay, then of course there are a bunch of general situation. I really cannot give you one single answer to say, hey, this is the you need to do approximation. Did you hear me well?
Oh yeah, I can hear you well now. Yes.
Okay, yeah, sorry about that. Yeah. So again, it's in terms of comparison, I mean, there's no unique approach, right? You can take a difference, you can take a ratio, whatever make your life easier, and then you try different things. Then approximation is some way we'll try a little bit to see if we can get any clear picture to make us a good argument about A bigger or B bigger. Right.
I see.
Sounds good. Yeah.
That makes sense.
Mm-hmm.
But I'm begging you that please, in the real final, please give us some hint that we could use approximation.
No,
Otherwise, I will sure use the explicit way rather than the
I
approximation,
mean,
and it will take longer time.
Yeah, my style is always like saying it. If something is really hard to derive, right? If you say, I'm not asking for like specific approach. I'd rather for you to think about any approach. okay, then if I tend to give you one approach, then that limits your thinking process. So again, I would rather to have you proposing any approach, even though that approach is somehow wrong to me. I will be more glad to say that, to see that, because you are trying. If I give you a specific approach, then you're going nowhere. Then I have no choice, just give you 0 points because you're doing wrong thing. You know what I'm saying? You the rather to have something not so specific, then you could, based on your thinking, based on your training, based on everything you learn from statistics or mathematics, to give me some comparison. Then normally I would say, as long as I see comparison, then I will basically give you quite good credits for that, even though I will write down this is a wrong approach, even though this is not the right thing to do. Okay. Yeah, I mean, this is about style. So, well, either way, right? So yeah. Okay, so that's the best I can give you. So if you think, well, you would like to really specific, I would think about it. Okay, but you will see it's more likely the open-ended question would be like in D or E, right? Very, very, very last of the question itself. Okay, good. Let's move on. Okay, I'm worried about we are going to be disconnected again. So let's do it quick. Okay, so number 2. Okay, and then basically number 2, it's talking about survival function. Okay, then you do have the original PDF. It's exponential. Okay, then I'm trying to estimate the survival function actually. That's my goal of this question is I'm trying to say, well, if I do have a PDF of the survival functions, PDF exponential, then I'm trying to estimating some quantity, which is transformation from original PDF. Then you possibly know which method I'm trying to testing you. Okay. So the number 1 is because of exponential distribution. Then I give you this guy right here, 2x bar divided by theta. This is exactly on the slides, right? So I'm not going to talk about this too much. So I think you guys should know this already. Your big one is show me that Q is a pivotal quantity, I think. Oh, no, I actually told you so already. No. Oh, yeah, I'm looking at solution right now. So sorry. So I'm asking, show me that Q is a pivotal quantity, right? Then you guys are doing final at home. So this kind of slides, there's really no reason this guy with this question cannot get 10 points, right? So again, this guy pivotal quantity, you actually need to show that the distribution of Q independent of theta. Okay, that's your goal, to show pivotal quantity. And then xi exponential theta, you guys see multiple times already, right? Summation xi follow gamma, then n theta, right? Then you divide it by theta. Basically, you divide it by theta on the scale parameter, become n1h. Okay, if it times 2, then times 2, then become n2. Okay, exactly your right hand side distribution independent of theta. So you can say that Q follow 2 summation xi divided by theta follow gamma n2. So independent of theta. So Q is a pivotal quantity. Okay. Of course, this guy right here, I can tend to write chi-square. Okay. Because chi-square basically is gamma. Chi-square is gamma 2n. So chi-square R by definition is gamma R divided by 2, then 2. So not surprising to see this guy, it's actually gamma 2n. Okay, you could write so as well either way. Okay, so that means using pivotal quantity, you could say so. The easy way of pivotal quantity is for us to easy to find quantile to quantile, A to B. Okay, gamma distribution, then A to B. Inside guy is 1 minus alpha. So this guy alpha 1, this guy alpha 2, alpha 1 plus alpha 2 is alpha. You can write so. And then the reason we like the pivotal quantity is it's easy for you to write A and B. Okay. There are two ways to write A and B. They are actually equivalent. For example, people might say, well, I'm going to using gamma's quantile. Gamma's quantile. Then n, then 2, then alpha 1 is. Then n, then 2, then alpha 1 is gamma's quantile. Then I can using B, using gamma quantile, so n and 2, then 1 minus alpha 2 is. Then gamma n and 2, 1 minus alpha 2. You could do so. And since I told you that gamma n2 is chi-square 2n, that means you can also write chi-square 1, chi-square 2n, 1 minus alpha 2. Either way, they are actually identical. Okay, then for doing that, basically just try 2n alpha 1. You have your pivotal quantity q divided by theta, then chi-square 2n 1 minus alpha 2. Then you put your theta in the middle. Okay, easy operation. Flipping, then switch around. Don't forget about bigger become smaller, smaller become bigger because of flipping. Okay, so eventually you will find that theta is lower bound, upper bound. Oh, this guy is lower bound. This guy is upper bound. Okay, you could find that theta is lower bound, upper bound of 1 minus alpha comes the interval bits. Okay, then in B, so I'm trying to ask you to find MLE of the survival probability P. Basically, it's survival function up to theta, up to x0 points. For example, 3 months, right? I'm trying to find P hat MLE right here. Okay, so as long as you can write down right here, become survival function. Like I told you, this guy is exponential minus theta plugging x0. As long as you can see right here, as long as you can see P is actually a function of theta, then you do know what MLE of that function of theta, right? Because I do know from the parent distribution, I do know how to find theta hat MLE. Okay? Then by invariance property, then PMLE is nothing but plug-in of the theta hat MLE right here. Making sense? Okay, so that means PMLE should be easy to derive. Then you will know that theta hat MLE right here is X bar. Okay, so then how do I derive in PMLE's large sample distribution then? Okay, then you can get started from theta hat MLE's distribution. Okay, then based on theta hat MLE's distribution, like I told you in the class, this guy is 0. Then I want inverse theta because it's ID. So looking for I1 theta, the information number, it's second derivative xi single PDF actually. Okay, when you find your MLE, you basically deriving your log PDF or log like a function already. It's not partial xi, it's crazy, partial theta. Okay, partial theta right here. Partial theta. Okay, as a second derivative, then put minus right here as information number. Okay, so you're deriving that. Okay, and then so if you feel like, well, if you don't know about whether or not the variance you derive is actually the variance you're looking for, another thing you could think about is what? To me, another thing you could think about is I put in X bar right here. What does that told you? What kind of math I'm going to use if I write it down X bar? In terms of large sample theory, it's nothing but minor variance of X1. What theory is this? Nothing but central limit theory, right? Okay, so it means you might not necessarily go with this complicated one, but it's general results. Okay, it's definitely doable in general. But whenever you see X bar right here, you can also use the central limit theory as well. That means root n X bar minus theta, then goes to D, then normal, then 0. I think variance 1 is theta squared. Okay. Yes, I think so. Okay, so that means eventually this guy right here got to be theta inverse 2. Okay, to make it correct. Okay, got to be there. You can double. Got to be theta. Some information number, and then okay, so right here is what? Hold on, let me make sure that. Did you guys still see my screen?
Yes.
Okay, sounds good. Because my computer just got kicked out of my. Okay, I don't see my whiteboard in my computer right now. Okay, so I will keep working on it, then taking the variance term right here is sigma square. Okay, good. So this is what method. This is nothing but delta method. Okay, so that means the goal is what is the G function, right? What G function could bring your theta to P? Look at this right here. How do you get theta and the P connected? G function is nothing but exponential then minus x then x naught right here, right? You see this guy right here, right? This guy right here, bring your theta to P. Okay, so if you can write down that G function, then everything just by derivation of G prime, then plug in theta, then taking square, then times sigma square. Okay, so the answer eventually would be the answer eventually. So this guy G prime theta, of course, it's x0 then theta so G prime theta, let's plug in theta directly. G prime theta eventually x0 theta minus 2 then exponential minus x0 divided by theta, right? Okay, then then you plug, taking square, you're plugging eventually this guy, I think, eventually equals to x0 squared theta minus 2, then exponential minus 2x0 divided by theta. Okay, so in B, really nothing but delta method is what I'm looking for. Okay, good. Then in C, things become more complicated. Right now, I'm saying is to testing whether the survival probability is higher than half, right? Given that x 0 points. Okay, so really just like saying it's I'm going to testing whether or not the P is bigger or smaller than half. So my null hypothesis written down as a P smaller than 0.5, smaller than half, or turn to have bigger than half, right here. I'm asking to find UMP test. Again, working on UMP test is nothing but what? Pattern recognition. You look at what it looks like. This guy is composite. This guy composite as well. And then one direction. If you see that, what theory you're going to use to find the UMP test? Color-Rubin theory. Okay, and why I basically is y1 to yn, yi definition is right bigger than x0. I'm asking using yi to do inference on p. Okay, so that means you based on pattern recognition, you are thinking about Color-Rubin theory. Right now, yi right here using y1 to yn to do inference, y1 to yn. And then not surprised to see what's the distribution of yi is. Nothing but Bernoulli, right? Because that indicator function. Only thing they have is possibility they have is Bernoulli. Then Bernoulli P is probability of x1 bigger than 0. x1 bigger than 0. Also P, right? P equals to probability. Let me pull that down. Bernoulli parameter P equals to Bernoulli P. Then P exactly equals to probability of x1 bigger than x0. Exactly survival function. Right? Good. Like a in B yet. Okay. So it means using Color-Rubin theory, again, I talked about Monday, right? Two things you need to have to work on Color-Rubin theory. One thing is sufficient statistics. Another thing is MLR property, right? So y1 to yn Bernoulli distribution, it shouldn't be hard for you to find out summation y is sufficient statistics, right? And then it also shouldn't be hard for you to having that is, for example, I have that joint PDF y1 to yn given p1, and then the other joint PDF or Oracle function y1 to yn given p2. Okay, let me write this p1 and then p2. Okay, you are going to show that is if p1 bigger than p2, if it's given condition, then the Oracle ratio is increasing function of the sufficient statistics. Okay, so again, if you really show that that's a decreasing function in some example, if you really pretty much show that it's decreasing function, then really switching back to increasing is nothing but you plus, you minus summation yi, then become increasing function. Okay, hopefully I'm making sense to you. So that means I always say it's increasing function because switching between increasing and decreasing, just put your minus on your statistics. That could become decreasing, become increasing. Okay, so then if you show that, then your likelihood ratio is a increasing function of yi, given that P1 is bigger than P2. Then using Karen-Rubin theory, okay, the UMP test, the rejection region of UMP test is what? Is your sufficient statistics, yi, say yi, hold on, yi, because I want to say yi, then bigger than some cutoff t, or cutoff c, anyway, it's constant, cutoff c, right here, okay? So by Karen-Rubin theory, we will know this is my UMP test, okay? Again, we haven't find C yet, but we will find C later on. So let me show that, maybe I can show this right here for you to get a better sense about what do we mean by MLR property, because I did not show that as much as I want. Okay, but the point is you can say, first of all, you can write that function, right, of the y1 to yn given p. Okay, y1 to yn Bernoulli, so that means nothing but consecutive product of pyi or yp, pyi, yeah. So take out, so I do a pyi, then 1 minus p, 1 minus yix. So this guy become p summation yi, p summation yi, 1 minus p, m minus summation yix. Okay, then you taking that ratio of LP1, LP2, LP2. You could basically, I want to jump a little bit, so P1 and then P2 summation yi, then 1 minus P1 and then P2. P2, 1 in summation yx. Okay, then if P1 bigger than P2, right here, you are trying to show that it's increasing function of summation yi. Not hard to see that, right? P1 bigger than P2, this guy bigger than 1. Okay, then the first term right here, increasing function of yi. This guy right here as well, right? This guy is smaller than y, but this guy is basically, when n goes to larger, this guy also increasing function of summation yi as well. Okay, so both are increasing function of yi. So that means that satisfy the MLR property, monotone likelihood ratio property. Yes. So that means you can free to use Karen-Rubin theory. Okay, so in this case, well, you might be able to cheat in a little bit. For example, it's you are going to, well, I did not teach other things than Karen-Rubin theory, right? You are going to say MLR property holds, even though you have no idea how to evaluate this guy increasing function yx. Okay, it's 100% for sure they are satisfied. Okay, so okay, if that's the case, then summation y bigger than c is a critical region. Then right now we are trying our best to find what c is, again using type 1 error right here. Okay, type 1 error supremum theta is in null space, right? And then probability of summation yi bigger than c. I tend to write, so of course we are not using theta, we're using p. But this guy right here, so-called theta in the null space means what? That means in your null hypothesis actually this, right? This is null hypothesis. This is null hypothesis. So it means ideally you write p smaller than 0.5. Okay, you look at this, and if we really have no idea how to evaluate supremum right here, like I said, good things always happen in the boundary, so you could say 0.5. Feel free to write so. I think 99.9% is going to be on the boundary. Okay, but you might want to think about it. Why actually, when p getting bigger, the whole probability getting bigger than in the right hand side, right? So basically, you are evaluate this probability. Okay, then imagine you are going to say this probability is increasing function of p right here, right? Then such that the maximum happens in the 0.5. Making sense? Okay. Then why this probability right here is an increasing function of p. Okay. Imagine your summation yi follow what distribution? Y1 to yn followed by Bernoulli p, summation y followed by binomial np. Right? So imagine a random variable is binomial np. When p increased, when your p increase, right here, okay, when your p increase, what does that mean by p increase? Or saying that it's p increase to go to 1, right? I mean, the boundary of the largest one, p is 1. Okay. So when p increasing, that means it's more highly likely you get y equals to 1, isn't it? Y equals to 1. Okay, making sense? So if we do have Bernoulli p, basically it's p is probability of yi equals to 1, right? You got larger p, that means it's more likely your y is equals to 1. That also means that your summation yi is more easily to bigger than threshold c right here. Making sense? So that's the reason why when p increase, your whole probability of summation y bigger than c increase, because when p increased, you will find more yi equals to 1 x, such that when you do summation, it's easier to bigger than c. That's a general explanation why the probability increasing function of p is. Okay, so that tells you that it's okay when p smaller than 0.05, when under null space, because this guy increasing function of p, then that happens in the boundary. So p equals to 0.5 x. Okay, then another thing is, could you actually find c right here that exactly make your probability equals to alpha? The answer is no. Okay, so I've been showing you Poisson case, right? I think Poisson case is the same thing as the Bernoulli case right here. If you do have your null distribution, something like this, this guy, for example, this guy I just join Bernoulli n 10.5x. That's why summation xi follows, right? Okay. Yeah. Okay. Finding that c, then make your type 1 error close to alpha. If you really set up alpha type 1 error as a 0.05. Then you find the column C based on that probability right here, right hand side probability, add up. You add up everything, then close to 0.5, 0.048. Okay, so then if you have this guy right here, then you're choosing that C. Yes. Okay, so that's the final answer of this column C. Okay, good. So any questions on A and B and C? Okay, if not, I'm going to talk about D. You guys still can hear me, right?
Yes.
Okay, thank you. Okay, so in D, again, another take-home question right here. So one can also using that large sample property in B. In B, basically deriving what? I mean, in B, basically deriving MLE of the P. Okay, then you could also find a approximate test for the null hypothesis in C. Derive any asymptotic test or comment on which test you would prefer. Okay, so I think if you do having that large sample property, for example, if you deriving P hat MLE right here, right, minus P goes to D, then normal, then 0, you do have your variance, I think, from B. Okay, say this is a variance of P hat MLE right here. Okay, let me just put it down V theta. Okay, pardon me on that. You can go back to the B to find what a V theta is. Okay, right here. Okay, so that's what we have in B. If you have that, the most easy of testing is what? Word type test. Word type test is nothing but root n P hat MLE minus P divided by square root of V theta. Okay, and then I think my solution key is wrong, right? This is, let me see, do I talk about, yeah, the solution key is wrong because I do having that null hypothesis smaller than 0.5. Yeah, so I think it should be one-sided test, not two-sided test. The solution key rounded two-sided test. Actually, I'll prefer one-sided test. Bigger than Z1 minus alpha. This is better answer X right here. Based on X sample, right? Based on X sample right here. The solution key written like two tails. It's actually not because I saw it's two tail testing. Okay, it's actually one tail testing. Yeah. Right. It's wrong. It's wrong. Yeah. Okay, should be one tail because I do saying that it's the alternative is bigger than 0.05. 0.5. Okay. So using this guy, one-sided test, I'm using two-sided test. Then that's it. Because it's as easy as what type testing is. Whenever you have an MLE property, then what type test is the most easy way to do that, right? You're just taking the divided by your standard, divided by the square root of variance. You got it. Okay. Then of course, in the solution I write down is, well, it's not, this is nothing wrong. You'll be able to do this, right? Because they are just one-to-one transformation. So this guy right here will give you the same testing as well. This guy will be theta actually. Square root of theta squared becomes theta. This guy will give you the same testing because the transformation is one-to-one as well. Which means that you are testing theta. Not actually, so this guy it's easier to write down it. You say that it's actually is x0 divided by log 2 it. Okay, then versus your null hypothesis. Oh, it's not bigger, it's actually smaller, also smaller. And then say that bigger than it's a 1-to-1, but does that, oh, you might reverse no. That's still increasing function with theta, I think. So small is still smaller. P is still increasing function with theta, right? This guy right here, log 2, something like that. Okay, but they're equivalent to this, right? They're equivalent. P smaller than 0.05, then versus alternative, P bigger than P is P, not theta. This guy is P bigger than 0.058. Okay, good. Okay, I'm losing my power, so hope I can finish that. Oh, there's no way number 3 could finish in a short period of time. Okay, so any question on the 2, A, B, and C?
Hi, I have a question.
Yes, go ahead.
About 2C. Yeah, it's a one-sided test, but we don't know the variance.
No, it's fine.
It's
Why
fine?
why variance is important?
Otherwise,
So
you can't derive the rejection region.
Hold on a little bit. Let me think about it.
The variance includes the data.
You're asking it if it's a one-sided test. You could still write down your critical region as one-sided. Why not? Your alpha still supremum of P smaller than 0.5, right? Then your supremum was still having a boundary, right? You know what I'm saying? Let me write it down right here. So eventually, even it's a asymptotic test, if you write down this, it's still write down supremum P smaller than 0.5 or 0.5, yeah. Then probability of your critical region, P hat MLE minus P divided by square root of B theta, then bigger than Z 1 minus alpha. You still do so, right?
Yeah, but how do you deal with the V theta?
Yeah, you plug in P hat.
Just plug in P hat?
Yeah. Either you plug in P, hold on. You could either plug in P hat or plug in P equals 0.5. So this guy right here eventually is probability of P equals 0.05. Right?
Why I can just plug in?
Plug in 0.05. Either way. In a word type testing, possibly people will think about plugging P hat. More like word type testing is. But in this case, it's okay to plug in 0.05 because under null hypothesis. It's a definition things. Either way will work. Either way is fine.
Under the null hypothesis, the P is smaller than 0.5, not equal to.
But you control for alpha.
Yes.
Control for alpha is you choosing that the worst case. You choosing the worst case scenario is P equals to 0.5. That means you have different P null hypothesis.
Oh, okay.
You're only choosing the worst one to do the testing.
I see.
You know what I mean? Yeah.
I see. Yeah. That makes sense.
Yeah.
Okay, thank you.
Yeah. Okay. So then go to 3. If I actually losing my power, okay, I still have 1 hour and 30 minutes to go based on my computer. So hopefully everything's fine. Okay, I forgot to bring my power cord upstairs. So let's hope we can survive. Okay, so right here it's number 3. It's not easy question at all. Okay, I do give you 2 distribution. One is PDF of y given x is x. So that means it's conditional PDF. Conditional on x, distribution of y is, then not hard to imagine your PDF got to have that little x in there because it's given is a conditional PDF. Otherwise, there's no reason to conditional on x. Okay, but it does look like exponential, right? Oh, you can call it exponential, I think. Okay, then I give also marginal PDF. Marginal PDF of x is another exponential. Okay, and then say y1 yn x and yn, you observe both x and y during your or in your monitors. Oh, this is like a spatial question actually. I mean spatial statistics question about air pollution. Okay, so in A, I'm saying is using the fact that the joint density function is, so you are working on joint PDF. The parameter will be alpha and beta right here, right? Well, shouldn't be hard for you to imagine what I'm saying, right? So, well, joint PDF is a conditional PDF. Then times marginal PDF. So really not hard to understand what I'm saying. Okay, then show that it's U1 and U2 are showing sufficient statistics. So I'm going to skip this. I think it's really easy for you to know that. I think really you guys shouldn't having any problem to deriving sufficiency, because sufficiency you can using factorizational theory to do so, right? Just writing down your joint PDF x and y, and then you will see that it's your summation xi attached with the beta, your summation y divided by xi attached with the alpha plus beta. Okay. So then let me skip that. So it shouldn't be hard for you to show that U1 and U2 are sufficient statistics. If you really feel confused about that, you can look at my solution key. You'll know what I'm saying about what I'm saying. It's how to using factorizational theory to show that it's something function of the parameter and then your statistics that give you sufficiency of alpha and beta. It shouldn't be hard to see that. I think in B, possibly it's most challenging questions. Okay, if I have U1 summation xi, I think, right, summation xi, yeah, and then U2 is summation yi divided by xi. Make sure that I got it correct. Yep. Okay, then you are going to show that covariance between U1 and the U2 equals to 0. Trying to show that they are uncorrelated. Okay, then eventually comes down to, because ID comes down to trying to show that these two guys are uncorrelated, I think. Okay, because this ID set up. Okay, then how to show this then? Okay, more likely if you are general person, you do this, right? You're trying to do covariance of AM or X and Y. You do expectation of YI, expectation to random variable, then minus expectation XI, expectation YI divided by XI. I think that's possibly everyone would go in terms of working on covariance between two random variables. And then this guy right here, okay, you feel like good, right? You feel good about it. XI cancel, EYI, then minus EXI, then EYI, then XI. Then you might be a little bit stuck. Okay, EYI possibly fine, right? EYI possibly fine. Okay, EY. So one thing I want to share with you is whenever you see that conditional distribution popping out in your master exam or any exam in the future, and then somebody asking you deriving about marginal expectation, one thing always comes up is what? Double expectation. That's for sure. Okay? It's never getting old. Okay? Every time you see the conditional distribution and somebody asks you deriving expectation of marginal, then you're always using double expectation. Then things become really easy. For example, right here, right, inside guy, because you do know that it's a conditional, you do have this, like a exponential distribution. That means conditional mean of y given xi is alpha plus beta xi. Making sense? Because this guy right here, this guy like exponential, this guy like a beta, right? Okay, then mean of that is beta. Okay, so that means alpha plus beta xi. And then you do have that alpha plus beta, then exi. And you also know exi from here. Okay, it's 1 over beta. So that means everything is alpha plus beta divided by times beta. Times beta. EXI is beta, so beta right here. That's EYIX. Okay? Then, how about expectation of YI given XI then? Okay? Then, again, trying to do a same trick, right? YI given XI X, right? Double expectation. And then hopefully you guys have good training on bios660. Okay. Because given right here means this guy's constant. So you can write this. Okay, good. So that means this guy right here, EIX1. You do know this guy, right? This guy is alpha plus beta XI. And then you cancel out, right? XI cancel. You don't have even deriving any function of expectation of anything. This guy could write it down as alpha plus beta directly. Okay, then using this guy, you got this guy, you got this guy is beta, you got this guy is alpha plus beta, this guy is alpha plus beta times beta. Again, this guy is 0. Right? The first one, alpha plus beta times beta from here. This guy coming from distribution of xi, and this guy is alpha plus beta from here. So both guys equals to alpha plus beta times beta. So this guy is 0. You show that. So that means U1 and U2 are uncorrelated. Okay, good. So I think I'm generous at the time. I only want you to show that uncorrelation, but you actually can show that U1 and U2 are independent. Okay, or actually it's xi independent with xi divided by yi. Okay, then how do I show this? It's a perfect question for meter number 1. Is because if the meter number 1, you will know independency is what? You say if I name this V, name this guy W, then you will know how do I show V and W are independent. Right? How do I show that? This guy basically using what? Nothing but transformation methods. X and Y. Then you find your inverse function and then find your Jacobian right here. Okay? I don't know if I will give you the same thing. I haven't written down any question yet. but I would be suspicious. I'll give you less to work on in the final. But I may change my mind. I just think about it may be bronze thing less. Okay, by any means, you could using the old trick to show that U and V are independent. Okay, so in the final, if you actually show that U1 and U2 are independent, such that U1 and U2 are uncorrelated, yeah, you could go ahead. That definitely get points. Okay, it's definitely the right answer. It's definitely the right approach to answer this uncorrelation questions. Okay, good. So in C, well, basically it's just deriving 95% constant interval, either approximate or exact. So if you're looking back to the master exam in recent years, this kind of question always popping up. Want you to finding 95% constant interval, either approximate or exact. Okay. If I were you, I would go for approximate every time, because approximate, hopefully have the same sense of mind. Approximate is usually easy to derive, right? Because you need to, because in order to deriving exact distribution, you do need to know quantities exact distribution is, which is usually hard to derive. Or you need to, like, know bunch of transformation things, for example, exponential theta, summation xi is gamma, okay? Or something like xi is Poisson, summation xi is Poisson and theta, something like that. You do need to know that also association between distributions. But usually approximate constant interval, approximate testing, you're always coming from what? Large sample normality is. Okay? And it's usually easy to do so because whenever it's normal, it's just like, doing what type testing, right? You just really do that kind of easy thing to handle either it's what type test or either it's complex interval, okay? Because when you're deriving MLE, and then you get that pivotal quantity automatically. Okay, so like here, so in C, right here, it really, but pay attention to what you are talking about. So we are talking about gamma as alpha minus beta x. Okay, so to deriving gamma as alpha minus beta right here, let me see how we do that. Okay, so this condition is more likely gamma hat MLE is alpha hat MLE minus beta hat MLE. Okay, let me see what do I have any trick? No, I don't. Okay, the reason for that is if alpha hat and beta hat MLE are dependent, then things become complicated because you really don't know about variance about gamma hat MLE. Okay, of course you can do in that, say, well, why not do less, right? So you would say, hey, can I do less? Gamma, could I do less? By writing, yes, but derivation is difficult. Okay, you don't actually know what this is. Maybe or may not, because you need to do your Laplace function in a parametric of a gamma x, which is usually difficult. You will know that these two guys possibly dependent. Let's see. Yeah, I think so. Okay, good. So if you're deriving alpha MLE right here, okay, you can actually find out that this guy is n over n summation I from 1 to n yi divided by xi then minus, this is I guess this is MLE. Okay, I think so, yeah. And then this guy eventually become U2 minus U1 divided by N. Okay, yeah, that's what I'm looking for. Then beta MLE right here, it's of course 1 over N summation xi. This is x bar, I think. Okay, become U1 divided by N right here. Right? Yeah. Oh, it's not alpha height and beta height are independent. It's actually eventually this guy right here. I can write down U2 minus U1 divided by N minus U1 divided by N right here. I can write that as a function of U1 and U2, and the U1 and U2 are independent. So such that I will know what the variance is. For example, it's U2 minus 2U1 divided by N right here, right? Or how about write this? Maybe I will just jump in too quick. So this guy is U2 divided by N minus 2U1 divided by N. Okay? So that means when you're deriving the variance of gamma hat MLE, that becomes variance of U2 divided by N minus 2U1 divided by N. By doing so, really nothing but 1 over N squared. You have variance U2 minus plus 2 for variance U1 x. Then you'll be easy to do that. Let me see if my intention is, I think so. Okay. Eventually you'll find out this guy right here. You could derive in that based on previous derivation. Another possibility, another easy way to see that is I can have write down root n u1 divided by n minus beta goes to d normal 0 then beta square, right? Because u1 is summation xi. This guy is x bar right here. This guy is x bar right here. Based on x, I can find that is sample property of x bar and then minus beta. And I can also working on U2 divided by N, then minus alpha plus beta. Because in the previous derivation, I say U2 is what? U2 is summation I from 1 to N, xi divided by yi. Okay? Again, this guy is your friend, right? Okay? And then this guy right here is nothing but expected value of x1, y1x. Then by central limit theory, I will know this guy is 0, then variance x1 and then y1 by central limit theory. Okay? And then you will know that this guy right here, you could derive it. Then this guy eventually is alpha plus beta squared. How do I deriving variance of x1 and then y1? Again, whole thing is conditional distribution. You do see a conditional dependent. You do see a conditional distribution from A and B. This guy nothing but what? I know how to derive expectation using conditional distribution. You should know that variance also be a formula, right? For example, variance expectation of x1, y1 given x1. Variance expectation, then plus expectation, then variance. Oh, I actually switching around, right? It's yxi, it's xi, yi. So, pardon me on that. So everything is yi divided by xi. Okay, y divided by xi, y1 divided by x1. So this guy, everything switch up. y1 x1, then y1 x1 given x1 is okay. Using that, eventually you will see this guy equals to alpha plus beta square. Okay, so by doing so, let me take a bunch of things out. Hopefully you can see that easily. Okay, if I take everything out, I'll write this equals to alpha plus beta then square. Okay, so such that this guy alpha plus beta square, alpha plus beta then square. Okay, so your target is gamma hat MLE, right? And then gamma hat MLE would be alpha hat minus beta hat MLE hits. So it means, yes. Okay, so if not, so eventually this guy become U2 divided by n minus U1 divided by n. That means from here, you do know this guy's Lysenko property. Okay, and then by here, you know this guy's Lysenko property. So it's right here. So I can write. So eventually, I'm trying to understanding minus gamma, right? Goes to D, then normal, then 0. Most likely, you don't know what. Most likely, you're trying to derive what a variance is. And then you also know that your gamma hat is U2 divided by n. So U2 divided by n. Then minus 2 U1 divided by n. Minus 2 U1 divided by n. Okay. So that means right here, you minus gamma, okay, goes to D, then normal, then 0, something right here. Again, you do your best to derive invariance, okay? But the point is, you do know that U2, and right here, okay, minus alpha plus beta goes to D, then normal, 0, alpha plus beta square. Okay, then you also know that square root of U1n minus U1n is beta, goes to D, normal, 0, then beta, then square. Okay, you know these two guys. Okay, you are trying to get to this guy right here. How do you do it? Doing nothing but you times 2 right here, become 2 beta, then become 4 beta square. Okay, then you do subtractions. You do this guy, subtract this guy. That means everything exactly the same thing as the mathematical operation is, right? Random quantity minus this random quantity, nothing but really alpha plus 1 minus 2 beta right here. Okay, then goes to D, then normal, because really nothing but this random variable subtract this random variable. So in terms of variance, nothing but plus. It's okay. Then you do know this guy is your gamma hat MLE. And then this guy, of course, is alpha gamma equals to alpha minus beta. Okay, that means this guy is your variance. As long as you're writing that down correctly, then how do you working on it to find your gamma's 95% constant interval, or 1 minus alpha, right? If you do writing down this, then nothing but the way I said it is, you could easily to write asymptotic pivotal quantity it. Because you do know asymptotically, this guy is going to follow normal 0, 1. Then automatically, asymptotically as a pivotal quantity. Then easy to find quantile to quantile. This guy Z and the Z. Right? A to B, pivotal quantity, A to B, quantile to quantile. Because my pivot is normal 0, 1. So nothing but normal 0, 1 is quantile to quantile edge. And then again, right here, okay, you don't know alpha and beta. If you don't know it, you do estimation. So that means you plug in about your MLEs, okay? Because MLE are considered estimation. The MLE are considered estimators of alpha and beta. You plug in consider estimators, the whole thing still goes to normal 0, 1 by Starsky. Okay, so that means then life even be easier, right? Eventually you put your gamma in the middle, then do operation, taking square root right here. Then you got your lower bound and then upper bound edge. Lower bound and upper bound. You got your lower bound, upper bound. Okay, because right here, if you plug in alpha by alpha head, plug in beta by beta head, then it should be easy for you to operate on to put your gamma in the middle by moving around over quantities. Okay, good. So indeed, assuming beta is known quantity, okay, then the right MLE of alpha, I want to save time, so I think alpha MLE should be easy to derive, right? Given beta is known quantity. So then you just doing that, deriving that join PDF or single. Let me see. Could I working on a single PDF? No. Yeah, you need to working on join PDF. Then by that join PDF, you do know alpha is fixed. You can deriving your alpha MLE. Then using the usual way of deriving MLE, you do differentiation on join PDF. Okay, and eventually, let me see. Eventually, alpha head MLE is this. Eventually, alpha head MLE. It's, let me see. Okay. Summation I from 1 to n, then yi divided by xi, then divided minus beta. Okay. So by second derivative, I think should be straightforward to see that, oh, we need to plug in alpha head. So you do second derivative, oh, you do your minus of information matrix. This guy plugging alpha head bigger than 0. I write J observed 1, so bigger than 0. Okay, but it's minus second derivative bigger than 0. How I'm trying to say is you need to plug in alpha head to see that. Okay. And then in E, just trying to show that you need deriving whether or not MLE is unbiased estimator. I think should be easy, right? Because you do from A, you do know what that is already. MLE, nothing but you put your n minus 1 summation I from 1 to n expectation of yi divided by xi, then minus beta. And then, yeah, a little bit wiki right now, so taking right here. Okay. And then from A, I think, from A, you do know the expectation of y divided by xi. Okay. And then, let me see. I think right? I think this equals to I from 1 to n. Expectation of yi divided by xi is alpha plus beta, I remember. Yeah, I think it's correct. Alpha plus beta or divided by n. No. Alpha plus beta. Then minus beta right here. So right here, this guy cancel out. Alpha plus beta minus beta equals to alpha. So then MLE alpha hat is an unbiased estimator of alpha. And then you are trying to derive the variance. Again, using the variance XY. So you will need this right here, right? Because when you're deriving variance of alpha hat MLE equals to n minus 2. Pardon me, I'm jumping. Hopefully you see that. Okay, because if you do this, beta doesn't important by variance. Okay, then this guy right here, it's n minus 2 summation I from 1 to n alpha plus beta then square, then become alpha plus beta squared divided by n. Okay, that's the variance of alpha. Of course, when you do your derivation MLE, you deriving this, right? You do deriving your J alpha, or no, yeah, J alpha right here. So in terms of Cramer lower bound, right? Right here it's D alpha. So you're looking for alpha. So there in the numerator is 1. And denominator would be what? Expectation of J alpha. It's right here. Okay. So like I said, it's always using second derivative when you do the denominator of the Cramer bound, because in the second derivative, usually if you're only using first derivative, you take a variance, you take square function, you take a square, you take expectation. I mean, it's really sometimes it's hard for you to deriving expectation taking something square. As I can see in the meter number 2, some of you actually taking square and take expectation. As you can see right there, it's so hard for you to do operation of the mathematics, right? So if you get lucky, you get clean version of the answer. If you are just you don't have good mood about deriving everything, everything screw up, then also expectation just really looks really weird. So keep one thing in mind: it's I won't give you something really weird in terms of answers. Bunch of plus and minus things. It's not going to happen. As you can see, everything is really clean in terms of the answers, right? So whenever you derive something, you find out it's really weird answers, please go back to check every line of your derivation. You may find something wrong during the derivation of answers. Okay, right here is, I think it's 1 right here. I think expectation of the observed information eventually, let me see, this guy eventually is n alpha plus beta then minus 2. Again, you will see everything Cramer bound is divided by n. If your Cramer bound is divided by n squared, that means you give too much n's in derivation. It's okay, good. So then you'll see that it's alpha actually reaching the Cramer bound. Okay. Then of course, the alpha hat MLE is a UNVUE as well, because the variance is a bias. The variance reach the Cramer bound. So then alpha hat is a UNVUE as well. And then I think in F, I think assuming beta is known, then you are trying to testing whether or not alpha equals to beta. Okay, then beta is known quantity, so beta is nothing but constant. So let me see. And then why I reaching that? I don't understand why it's function of beta then. Oh, so my solution key may be wrong, right? It should be function of alpha. Right. I think I make something wrong. Yeah. The solution key should be wrong. It should be function of alpha. For example, it's right here. I'm trying to talk about it. Alpha is beta is constant. So you really estimate alpha and then to see alpha equal to some constant or not. Okay, then when n is large, so I'm asking you about critical regions of LRT, then the same tree, just the same thing, right? So it's not easy to deriving, say, LRT yet. So this is your data right here. And then -2 lambda, your data right here, right? So in terms of LRT, you do know that you're writing down lambda. Okay, you could write your definition of lambda by any means, right? And then you take minus log 2. You take a -2, taking log on lambda. Then you know that it's asymptotically follow chi-square distribution, and then cutoff would be chi-square 1, and then 1 minus alpha is okay. And then of course your lambda, if you really want to write it, it's fine as well. You supremum, right? Supremum based on null space. Then supremum based on overall space. You have your right now only have alpha, right? Because beta, again, beta is known quantity, right? Yeah, I think so. So that means this guy right here. Oh, maybe I mean still right. So let me see. Okay, let me see. I don't. So this is LRT lambda, and then your null space is alpha equals to beta. So that means this is your null space right here. In terms of MLE, only have a single value of alpha, right? And then your overall space, that means it's not no restrictions, would be your alpha hat right here. Okay, you could write so, and then you taking log lambda, this lambda, nothing but having that log, the logical function, log alpha headed. Okay, by any means, this is a key point. It's when we take -2 log lambda, then bigger than chi-square 1. That's LRT. Oh, yeah, I think I'm still correct about the solution key. Okay, the reason for that is, okay, so if in terms of score test, right? Score test using the property of the score function. So you have your slides, and so you have your cheat sheet, for example, then you would basically know that it's, let me square root, right? So square root u divided by n, u as a function given their null hypothesis, right? So given null hypothesis, alpha equals to beta. That reason why I say u beta. So then that guy's mean 0. That guy's mean 0, so -0, and then goes to D, then normal 0. This guy is I1, not I0, given that alpha equals to beta. So this is a large sample property of a score function. Then you're using that to do your, it's ID, right? It's the ID, so I think it's the ID. Okay, so then you're using the property to construct it as score test, and then divided by square root of I1, then beta right here. And then asymptotically, because that can follow normal, is bigger than Z1 over alpha over 2x. That's a score test. Nothing by using the property of the score function asymptotically right here. Okay, then of course you can write the same thing right here. You can write down as u beta divided by n, then cancel up, become root n. You could put root n down, then you could put root n down, then become square root, n times I1, then beta right here. And you also know that what is like n times I1 beta is nothing but In is observed or expected information, accumulation from n observations right here. Okay, so you have different options to writing so. Okay, then even easier if you this is a score test, right? Score test. And how about word type test? Word type test using the property of MLE. This is the inverse right now. Okay. So right here, since I say null hypothesis alpha is beta, right? Alpha is beta based on null hypothesis. It's okay. So then the word type testing rejection region, just using that right, divided by square root I1 inverse alpha, it's bigger than z alpha over 2. Of course, under null hypothesis, this guy is alpha become beta, alpha become beta, alpha become beta. Okay, good. And then, of course, I said people using different version of the denominator of the word type test. Okay, you could plug in I1 inverse, you could plug in J1 inverse as observed information as well. Or you could put n down right here. Okay, so for example, well, that's actually the same thing. It's people would write as so head. You would put n down, right? So read nothing but put n down and become 1 inverse I1, then beta, for example. You put root n down, right? So alpha head MLE, then minus beta. Then right here, people tend to say you could also write inside guy become IN as well. So hope you can see that right here. You bring one more n inside inverse, then become times n. The whole thing is inverse right here. Okay. You could write also your denominator as IN beta, IN alpha inverse as well. Okay. Again, you could also replace this guy become JN beta using observed information matrix as well. So there are a bunch of things you can do in the denominator of word type testing. Okay, good. So let's stop it here. It's 5:22 already. It's too late. And then, any questions?
I have a quick question for
yes.
part C.